So now let's talk about divergence. So a definition. The divergence of the vector field F, which will be mi plus nj, is defined to be the dot product of the gradient with the vector field. So it's the partial of m with respect to x plus the partial of n with respect to y. Now here, you're taking a dot product, which is not a vector. So in the end, you should be getting a scalar, not a vector. And then how do you do it for a vector field when you have three variables? The divergence of f, x, y, z, it's mi plus nj plus pk is defined to be, it's still the dot product of the gradient and the vector field, but it's now going to be the partial of m with respect to x, the partial of n with respect to y, plus the partial of p with respect to z. And if the divergence of f is 0, then f is said to be divergence free. Okay, so let's look at an example here. Let's find the divergence at the point 2, 1, negative 1 for the vector field F. Let me go ahead and move that to the next line. The vector field will be x cubed y squared zi plus x squared zj plus x squared yk. So remember that this is your m, this is your n, and this is your p. So to find the divergence of f, you're going to take the partial derivative with respect to x of m plus the partial derivative with respect to y of n plus the partial derivative with respect to z of p. So here I'm going to get 3x squared y squared z, and these other two partial derivatives, these are 0. So this is my answer here for the divergence. Oop, actually no, because I was asked to find the divergence at a point, so we need to plug in our point 2, 1, negative 1, 3, 2 squared, 1 squared times negative 1. So you're going to get negative 12. So there's my divergence at that point.